Alright, this Regents chemistry video is on the combined gas law. So what the combined gas law is used for is basically to track changes that happen in a gas based on pressure, volume, and temperature. So the variables in this equation, P is pressure, V is volume, and T is temperature. Very important with the temperature here, it always has to be in Kelvin when you go to use this equation. So if you have a Celsius temperature, you have to convert it to Kelvin. Remember, our formula for that is Kelvin equals Celsius plus 273. So just add 273 to the Celsius temperature to get Kelvin before you plug it in to use this equation. If you have your temperature in Kelvin already, then you can just use that. You don't need to convert it at all. It needs to be in Kelvin when you use the temperature in this equation. So what we're doing here, we're basically comparing a before and after case of a gas to see if we have some changes in, like, let's say pressure or volume or temperature or all three. What's that going to do to the pressure, volume, and temperature of the gas after those changes happen? So the last thing here is if you have a variable that's constant, you drop it out of the equation. So if we have, let's say, some changes in pressure and or volume at a constant temperature, so temperature would then drop out of this equation and we'd end up with P1 V1 equals P2 V2. So if we have, let's say, a constant volume, we'd drop volume out of the equation and then we'd have P1 over T1 equals P2 over T2. So whatever variable, if it's pressure, drop out pressure, and we have V1 over T1 equals V2 over T2. So whatever variable it is, we just drop it out of the equation and use only the other two variables that there are. So let's try out some problems with this formula and see how we do. So if we have a bag of potato chips packaged at sea level at 1 atmosphere and a volume of 315 milliliters, the bag is then transported to Denver where there's this new pressure. What's the new volume going to be? So right off the bat, we should see there's no temperature involved here. So we're going to leave temperature out of the equation then. So this equation, instead of being P1 V1 over T1 equals P2 V2 over T2, is now just going to be P1 V1 equals P2 V2 after we drop the temperature out of the equation. So what we have to do is basically sort out what information means what in this problem. So one of the first things you want to do is you have to know the units that are measurements of each variable in this equation. So for pressure, the possible units that you're likely to see are atmospheres, or pascals, or kilopascals. For volume, you could see milliliters or liters. Generally, I mean, gallons would be another unit for volume, but we generally stick to the metric system here. Temperature, you could have Celsius, degrees Celsius, or Kelvin, but remember, we always need Kelvin here. So if you have Celsius, convert it to Kelvin. So these are the units you want to watch out for in these word problems to try and pick out what each variable means. Because what we're going to do now is kind of list out all the variables that we have in this problem, all the numerical information we're given, and then basically just plug it into this formula. So what we have is the initial pressure, P1, when it's packaged, is 1 atmosphere. We also know the initial volume, V1, is 315 milliliters. And then our final information that we have a new pressure, P2, is 0.775 atmospheres. And then we're looking for V2, that's our unknown. So we're going to be solving for, again, the new volume here, so V2 is what we're looking for. So now we have all the information now. We've kind of picked it all out of the problem and put it in terms of these variables, so all we have to do now is just plug this all in to our formula, which we said once we dropped out temperature was going to be P1 V1 equals P2 V2. So we have 1 atmosphere, P1, times 315 milliliters is our V1 equals 0.775 atmospheres times our V2, which is our unknown. So the unknown always just stays as a variable, and that's what you're trying to solve for. To solve for V2, we just want to get it by itself. We want to isolate it. We do that by dividing 0.775 on both sides. And so you should get V2 here equals 406 milliliters. Alright, so to review the steps here, we want to pull out all the information in this problem and list it out in terms of what variable it is, and then just plug those variables into the equation and solve. So let's take a look at another example here. We have a balloon that has an initial volume of 1.8 liters, and the temperature of the balloon when it was filled, so again our initial conditions here, was 20 degrees Celsius and the pressure was 1 atmosphere. So we got a bunch of information there already. We have our initial volume, V1, is 1.8 liters. We have our initial temperature, T1. It's not 20 degrees because again we need to convert that to Kelvin, so Kelvin would equal Celsius, which is 20 plus 273, so that would give us 293 for our temperature. For our pressure initially, we know it's 1 atmosphere, so there's not much to do there. And we can list out our final information now. We have it rose 3 miles into the sky where the pressure is now 0.667 atmospheres. So P2 is 0.667 atmospheres. And we have our T2, which is negative 10. So again, we convert that to Kelvin by adding 273. This would give us 263 Kelvin. And then our V2 is our unknown. So we have all our information now. We've got all 6 pieces of this equation. We're not going to drop anything out this time. All we're going to do is plug in. So our P1 is 1, our V1 is 1.8, and our T1 is 293. Our P2 is 0.667. Our V2 is our unknown, so we leave it as V2 over T2, which is 263 here. So to solve this, there's 2 ways you can do it. Well, there's more than 2 ways, but the 2 ways that you're going to be most familiar with, we can either multiply, we want to get V2 by itself basically, so we can multiply this 263 on both sides, and that would get rid of that, and then divide the 0.667 to both sides and get rid of that. So basically we would multiply by 263 here on both sides, and then divide by 0.667 on both sides, and that would get rid of both of these terms. What you could also do is cross multiply, and we would have then 263 times 1.8, and then set the crosses equal, and then we have that equals 293 times 0.667 times V2, and then divide away to get V2. But whichever way you like to do it, what you should come up with here is V2 equals 2.42 liters. So again, we're just taking this word problem here and pulling the information out and listing it all in terms of the variables, and then from there it's very simple. We just plug these variables into the equation, which again, in case you didn't write it down, is P1 V1 over T1. T1 equals P2 V2 over T2. So then it's just algebra from there to solve. So if we check out another example here, we have an airplane with an internal pressure initially of 1 atmosphere and a temperature at 25 at takeoff. So these are our initial conditions that we've established. If the temperature of the plane drops to 17 degrees Celsius during the flight, so this during the flight means that we now have some after conditions, so there's our separation there. What is the new pressure? So we're solving for P2 is our unknown. So if we list out some of our information here, we have P1 is 1 atmosphere, and we have T1 is 25, but not Celsius. We've got to do 25 plus 273 would give us 298 Kelvin, because again we can't use Celsius, we have to use Kelvin in this combined gas law. So our new temperature is 17 plus 273 would give us 290 Kelvin, so we can now just solve for P2. We've got all our information. You'll notice that no volume is involved here, so we're going to drop that out of the equation. It'll be P1 over T1 equals P2 over T2. So to solve here, we just plug in, we've got 1 over 298 equals P2 over 290. So we can just multiply both sides by 290 here, and that would give us P2. You could also cross multiply, that's going to be an extra step here, but however you like to do it, we just solve for P2, and P2 would then be 0.97 atmospheres. Alright, so we've got one last example here. So, some of you may have heard of the bends. This is kind of a condition that some divers get if they come up from deep sea too fast, because down in deep sea it's really pressurized down there. There's a lot of water pressure on these divers when they go up there. So if they come up too fast, there's going to be this extreme change in pressure as they come up. So if we look at this, it says the initial volume of the bubbles in the diver's blood are 15 milliliters. So our V1 is 15 milliliters, and the initial pressure is 12.75 atmospheres. So a normal atmospheric pressure is 1 atmosphere, which is our final pressure. So you can tell this initial pressure is very, very pressurized compared to the air pressure that you feel every day, which is 1 atmosphere. This is 12.75. So this is going to be a drastic change in pressure here. So what we're solving for is what is the new volume of the bubbles after the diver has surfaced. So V2 is our unknown. So the variable we're missing here is, again, temperature. So we're not going to use temperature in this equation. It'll be P1 V1 equals P2 V2. So this will be 12.75 times V1, which is 15, equals P2, which is 1, times our V2, which is our unknown. So there's actually not much solving to do here. This V2 times 1, we could just drop that 1 out and we still have V2 here. So we multiply 12.75 by 15 and we get V2 equals 191, and that's going to be in milliliters because that was our original measurement up here. So if you were unable to solve any of these gas law problems, just go back to the beginning of the video and try some of these examples again and work through them on your own. But I hope this was helpful on learning how to use this equation. Thank you.